Hello and welcome to week 9. We've been talking about the electromagnetic spectrum, electromagnetic radiation, and specifically remote sensing. Well, we have courses that do a deep dive into what remote sensing is all about, Geography 3440 and 4440. This here is to give you a taste of what's possible and what is out there and what a satellite image even measures and looks like, and to give you some hands-on experience to look at and manipulate them at least a little bit to get started. If we look at the image that we have on the screen right now, we have the continuum of electromagnetic radiation represented nice and cleanly in diagram. So if we think about the scenario here on the far left of the diagram, we have short wavelengths. That is the distance from crest to crest or trough to trough of the waves of electromagnetic radiation are really, really short and increasingly shorter as we move to the left. We call that shorter wavelength electromagnetic radiation. And as we move to the far right side of the diagram, that distance between successive crests or troughs gets longer and longer, and we say that we have longer wavelength electromagnetic radiation. So depending on where we are in this continuum, the nature of that energy is going to be different. It's going to have its own specific characteristics and properties. As we move towards longer wavelength electromagnetic radiation, we have less energy, and as we move to the shorter wavelengths, we have more energy. The neat thing is that there's tons of energy out there that is completely invisible to the human visual system. There's only a very narrow range of wavelengths that our eyes can detect and sense, and that we can make sense of in terms of what we call sight and vision and the ability to see color. That visible part of the spectrum is shown here in an incredibly small region that spans from about 400 nanometers to 700 nanometers of wavelength length. As we get to things that are longer wavelengths, things that are invisible to the human eye, we get into infrared, which is often referred to as near infrared and middle infrared, depending on whereabouts in this part of the spectrum you're located. Microwaves, radio waves, things here get into the order of meters to even kilometers in terms of their wavelength. As we get shorter than the blue and indigo and violet parts of the spectrum, we get into the ultraviolet, we get into X-rays, gamma rays, cosmic radiation, things that we're lucky to be shielded from with the atmosphere that we have here on Earth. The visible part of the spectrum, this looks like a rainbow, and it is. It's splitting the energy across a series of wavelengths for us to see various colors. And we can remember the order of colors by the sort of term Roygbiv. I don't know if you've heard of this before, but Roygbiv, red, orange, yellow, green, blue, indigo, violet. So from longer wavelengths to shorter, it's a way to remember the order in which these wavelengths occur. So to keep in mind, we have short wavelengths, high energy, moving in this diagram over here to longer wavelengths, lower energy, and it's only this small region in the middle here that is visible to the human eye, but remote sensing satellites build detectors. Well, the sensors don't build the detectors, they build sensor detectors and put them in the satellites so that we can actually measure very specific regions of this spectrum and acquire images that characterize how that scene was reflecting energy in the specified range of wavelengths. So let's then turn our attention to a paper that was written by some colleagues of mine. I'll give you the full citation for this later as I add it on to the presentation. But this summarizes what some of the satellite sensors that are out there, what parts of the spectrum they're sensitive to. So across the bottom we have the wavelength of the electromagnetic radiation. Again, from 400 to about 700 is the visible part of the spectrum. Then we get into the near infrared, and we get into the shortwave infrared, and eventually out here we get into the thermal parts of the spectrum. The lowest line of data here indicates the specific spectral bands that the multispectral scanner system satellite sensors were sensitive to. So they were acquiring data here in the green, the red. There were 2 near-infrared channels and a thermal channel that they were collecting satellite imagery for. That means that every time an image was acquired, there would be one band or one layer of the image that told you how the green part of the spectrum behaved. There would be a second layer that told you how the red part of the spectrum behaved. 2 separate layers, one for each part of the near-infrared spectrum, and then one for the thermal. As the Landsat series of satellites evolved and sensors and detectors got better, we have the thematic mapper series, and we see the specific bands that it was sensitive to, the enhanced thematic mapper plus, and then the OLI sensor, which is the most recent. And you see that some of the bands have shifted. Sometimes the width of wavelength ranges that they're sensitive to have changed, and we've also increased and added in additional channels that didn't necessarily exist in earlier versions. What's really quite neat is that the ETM Plus, which is an imaging platform that we're going to look at some imagery from in just a moment, has a blue, a green, a red, a near-infrared, 2 shortwave infrared, and a thermal image that are provided with each scene that you acquire or download. So it takes the entire visible part of the spectrum and it actually acquires 3 different images. One that tells you how reflective the red, another that tells you how reflective the green, and a third one that tells you how reflective the blue parts of the spectrum were. The faint gray lines in the background tell us how transmissive the atmosphere is to those wavelengths of electromagnetic radiation. So when the bars are high in the gray part, it means that a lot of that energy is able to pass through the Earth's atmosphere. Areas like here, where there's virtually no transmission, there's no benefit to putting spectral channels in here, because when you're trying to measure energy in space, you're not getting it. It's not reflecting back up through the Earth's atmosphere. So the number of bands and how wide they are relative to each other tell us what energy is being measured and recorded on those specific bands. What's cool is that we can take any 3 bands and we can assign them to the blue, green, and red color guns to falsely color any spectral channel, even if it's invisible to the human eye. We can give it a color and we can produce color composite imagery. So we could take the green, the near infrared, and a middle infrared band and assign each one a red, green, or blue color gun and produce a color image, so that we can now see and perceive the patterns of the energy interactions at the Earth's surface that we simply don't normally see with our eyes. This brings us to the idea of color representation and RGB, or red, green, blue. And what I'm going to do is I'm going to make this bigger, just because we can see it a little bit better. And imagine now that we have red, green, and blue color guns, and each pixel in our image is like a number that tells us how much of a specific color we're going to turn on. So if we have a red, a green, and a blue image band, 3 bands, let's imagine the very top left corner pixel. There's going to be a number in each pixel from each band. So if we look at the value of the red band, maybe what we see is a number 210. If we look at the green, the corresponding green value in the same geographic location, but it's going to have a value, and maybe it's got a number of 74. And the blue band might have a value of 251. The resulting color is going to be this magenta color. So we, by individual pixel, look at the band value that we're applying to the blue, the green, the red color guns, and it adjusts these levels to produce the colors that we see. So let's take a look at some hypotheticals. Imagine the green and the blue color guns are both set to 0, but the red is set to 255. We end up with a pure red pixel. Obviously, if red is set to 0, green 0 and blue 0, we get black. But if the green is 255, we get a green pixel. If only the blue is fully turned on, we get 255. Imagine that we have like 3 dimmer light switches and we change how much of each red, green, and blue light we're turning on. We're able to produce all sorts of colors simply by playing around with these sliders and these colors. And if all of the 3 are 255 or fully on, we get white. So we have the ability to play with these 3 different color sliders to produce every color that we can actually produce on an image. And remember that the amount of red, the amount of green, and the amount of blue light is determined by the numbers that are stored in the pixels on the individual bands that we are trying to view. This leads to this idea of the color cube. And imagine that the back far corner, the one that we can't really see, but where the X, Y, and Z arrows would all come together at an origin point. That would be like having all of the sliders turned off, and we would have black. Imagine Z here represents the amount of blue light. So if it's all the way at the bottom, it's 0. And as we increase, we go all the way up to full on or 255. If only the blue slider is turned on, but the other 2 are off, we end up with blue. If the blue is off and Y is off, but the red or X is all the way on, we get pure red. If we have only Y all the way on, or green, and blue and red are off, we end up with a perfectly green pixel. Now, we know that we can have these sliders in any ratio, and depending on how much red, green, or blue light we turn on, we're going to plot somewhere inside this color cube, and it's going to define the color that a pixel is going to be shown as. So as we adjust which bands we put into the blue, green, and red color guns, we're in essence telling the software how to set the sliders for each pixel to produce the colors that we see on our output display. I'm going to minimize that for a moment, and I'm going to show you some actual imagery. In just a second, I'm going to bring up Google Earth Pro. This is our campus here, but what I'm going to do is I'm going to move all the way over here to the border between Ontario and Quebec, and we've got Pembroke and Petawawa, and we have Chalk River. This is where a lot of the atomic energy research in Canada is being taken place, and so on. And it's this region for which I have some satellite imagery that I'm going to show you. So we're going to open up ArcMap, and we're going to have a blank canvas. There's nothing loaded in here yet. And I have a satellite image that I've taken a small subset from, because otherwise it's really large and it takes a little bit longer to process. But I'm just going to drag in this subset from Landsat 7 that represents part of that scene that covers Petawawa and Pembroke and Chalk River and so on. If you look at this, it doesn't look great. We can right-click on the actual layer and go to Properties. And I'm going to put the Properties tab up here. And notice that right now we're looking at an RGB, or red, green, blue color composite. That is, we're taking 3 bands, we're assigning one of them to the red, one of them to the green, and one of them to the blue color guns. Those color guns don't necessarily mean that they represent the red, green, and blue parts of the electromagnetic spectrum. We can take any part of the spectrum and assign it to any color gun. This is a subtlety that we need to keep clear. Right now, the way that it's being shown, the Landsat blue channel, so 450 to 520 nanometer wavelengths, are being assigned to the red. The green is being assigned to the green, and then red is being assigned to blue. It's a weird combination that doesn't really help us very much. If I went to the Symbology tab of the RGB composite, these are our red, green, and blue color guns. And from these drop-down arrows, we can choose which bands we assign to each color gun. So let's go and assign the red band to the red color gun. We're going to assign the green band to the green color gun. And we're going to assign the blue band to the blue color gun. And we're going to click Apply. We're also going to go and click on standard deviations. Yes, we need to calculate statistics first. And we're going to click Apply. Okay. I'm just going to close this so we can see what's happening. If you were an airplane flying over this region, this is what the scene would look like to you. You know what I'm going to do? I'm just going to make this a little bit narrower so that we can see this a little bit larger. I'm just going to zoom in a little bit here. I'm using the wheel on my mouse to scroll, but it's very much possible to go in and use the zoom in and zoom out tools on your toolbar. And if you want, pick up the hand and then drag around and look at different parts of the image. I'm going to provide this data for you so that you can do this as well. So this is what it would look like. The water, it looks blue, vegetated areas look green, bare ground looks brownish. These really bright areas are built up, often paved sites. These are things that the way that we're normally observing the landscape is one way to assign the color or the bands to specific color guns. But it's not always the most effective way to look at the landscape, particularly if we have data from beyond the visible part of the spectrum. So now let's go and look at something that is otherwise invisible to the human eye. We're going to right-click back on here and go back to Properties. And again, I'm going to put this up here just so that we can see it a little bit better. And now into the red color gun, I'm going to put in the near-infrared channel. Into the green color gun, I'm going to put the red band. And into the blue, I'm going to put in the green. If you look at this image, you can see that it's a little bit hazy over here. The blue channel tends to pick up a lot of atmospheric interference, and the band is often a little bit contaminated with atmospheric effects. Hopefully by going to longer wavelengths, we're going to minimize some of that effect, but also enhance other elements of the image that we're able to pick out that normally we wouldn't see with our human eyes. So I'm going to click Apply. I'm going to try to look at a histogram. Oh, too much. No, sorry, not gamma. Aha, okay, percent clip. I'll talk about those in just a moment. So now we're looking at a classic false color infrared representation. So our infrared is being shown in the red color gun. And if we think about vegetation. Imagine you've got this nice green leafy tree, it's growing really well, lots of chlorophyll. That plant, that leaf, reflects tremendous energy in the infrared, but very little in the red. So if I look at this and I see lots of red on my image, it's because the near infrared is doing a lot of reflecting. It's boosting the values in the near infrared band. If the near infrared values are low, then we're not going to get as much red. That red slider is going to be low. It's not going to show up here in red. This combination is really useful for looking at vegetation abundance and vegetation health. So if we look at this, obviously in here, this we know is water, appears really dark because water absorbs really well all wavelengths of electromagnetic radiation. So it's like all of our sliders being really, really low. So we end up with something that's black. If, however, the red, or the near infrared in this case, slider is really high, tends to mean that we've got really high vegetation components, and these become areas that we can be quite confident that have vegetation. So it's a different way of observing the landscape than if we were to look at it only with our human eyes. Now we're starting to see some details inside these built environments. We can see some roads, we can pick out sort of urban structures in this setup that otherwise we wouldn't see very well. So we can go in and play around with other combinations and see what these things look like. Maybe we're just going to play around with some different bands and see what happens. Maybe not so great, but maybe highlights specific elements. It sort of washes out everything that's on land versus things that are water, but it picks out these urban built-up features and shows them in this purpley color. The neat thing is that we can assign different bands to the various color guns to try and emphasize or de-emphasize certain characteristics of our landscape. So we very clearly have a different sort of combination of things going on over here. The urban is sort of being picked out. All the vegetation, slightly different tones of green, are sort of all being sort of muted out here. But we have the ability to play with the different combinations to see what the effect is. And depending on what you're doing and why you're doing it, you may find that you've got very different sort of combinations that help to highlight specific characteristics. So this area in here behaves quite differently than what's around it. This water here is very different than this water here. The urban area now is really popping out. The road here is again popping out from the surrounding environment. The different sort of statuses of the vegetation component in fields is being picked out differently. So as we're trying to understand what it is that we're looking at on the ground, and we play around with which spectral bands we put into which spectral color gun, or sorry, into which color guns, we change the way that the image appears. And it's to help us see patterns and interpret things a little bit better. So that's one part. I'm going to now open up ArcScene. And ArcScene is designed for looking at things in 3 dimensions. I'm going to drag the same image that we were just looking at into ArcScene, and notice that it's drawing it in this 3-dimensional oblique perspective. When we pick up this navigate tool, we can hold down the mouse button and we can pan this thing around. Notice that if I put it right edge on, it looks like a nice flat pancake. There's no real 3-dimensional aspect being displayed here at this point in time. We can do the same thing by going to Properties, and we can change which bands we want to look at. So let's go back to false color infrared, because this is a standard way of looking at landscapes, particularly vegetated landscapes. We can zoom out, we can zoom in, we can use this little bird fly tool, and we can sort of move around and look at this image from different perspectives. We can hit escape to get back out of there. But what I want to do is now emphasize the pixel values here into a third dimension. I mean, it's possible to add a digital elevation model and put this image on top of it, and it looks really cool, but also for visualizing and interpreting the digital numbers that are in the file, what we can do is go to Properties, and we can go to Base Heights, and under this little File Open tab, we can choose the same image that we're looking at. I'm going to click Add, and I'm going to accentuate or vertically exaggerate by 15 times what that surface looks like. We can hit OK, and it just takes a second, but notice now that we're starting to get some peaks. I'm just going to zoom in a bit. And what it's doing is it's looking at the values in the file, and it's drawing them in 3 dimensions if the values are big, and it keeps them lower if the values are small. And you might say, well, why is that important? Well, if we zoom in, it allows us to very quickly see features that might otherwise be a little bit subtle, a little bit difficult to pick out, but this linear feature here, that's our road that we were looking at. But it pops out of the landscape because the values here are higher than what are in the surroundings. The urban built-up areas are popping out because they're higher than their surroundings. We can start to pick out sort of trends of how this surface behaves spectrally by accentuating in 3 dimensions what the values in the file are. And again, I'm just going to go one more time, and I'm going to change the bands that we're looking at, and I'm going to go back to a classic true color, so the same spectral channels that correspond with the same color guns. And click Apply. And this is basically what we have from the visible part of the spectrum. We have an environment where the built-up areas now are showing up much higher than the rest, and it gives us a way to detect and interpret things. So I can see something happening back over here. Maybe we can fly towards it. And then I'll just zoom out a little bit and grab the navigate. And if we look at this, we can see that there's this ridge that's coming through here with slightly higher values on it, and that is a road that's traveling up along the side of this meandering river and stream. So things that might be visually hard to perceive when they're flat, the third dimension and playing around with the color might help to accentuate those things just a little bit more to help with our interpretation of what's inside the satellite image. So now, if you think about multispectral data, you think about the spectral channels, what parts of the spectrum are they representing? We can choose any 3 bands and look at them as a color composite in RGB, where the cell values from the corresponding layers control the color sliders that tell us how much red, green, or blue light correspondingly to use to represent each pixel. We can observe color imagery. But we can also convert what that looks like into 3 dimensions so that we have even a richer understanding of the underlying data set that we're looking at. So until next time, have some fun with some remote sensing.